So today we're going to talk about graphing polynomial functions, and then we're also going to talk about even and odd functions. Oh yeah, and do please fill out the class attendance form when you have a moment. That goes for the people on Zoom as well. Please fill out the class attendance form. So just a few things, some names, some names really, or nomenclature, if you want to call it. A line is a polynomial of degree 1. And actually, I should even back up just a little bit. A horizontal line like y equal to 6 is a polynomial of degree 0. It's not very exciting, but it is true. Thanks. So a horizontal line like y equals 6 is a polynomial of degree 0. And you can see, or maybe you can't see because I didn't write it, but you can imagine that the power of x that isn't written there is x to the 0th power, because x to the 0th power is equal to 1. So I don't need to write the x to the 0th there, but it is there. So you could think of this, if you really wanted to, as y equal to 6 times x to the 0th. Thanks. So that's kind of one special case. A horizontal line is a polynomial of degree 0. But other lines, like f of x equal to x, f of x equal to 2x minus 3, y equal to 6x minus 4, those are all polynomials of degree 1. And again, the degree is just the highest power of x that you have. So I could write a power of 1 on each of these to make it a little more explicit, but we don't usually do that because we're lazy. Or at least I don't do it because I'm lazy. I can't speak for you all, but you're not usually writing x to the first. Parabolas, quadratics are polynomials of degree 2. That means the highest power of x is going to be 2. And I should say, when we talk about polynomials, all of the other powers have to be positive integers. Can't have any negative powers, can't have any fractional powers, can't have any other weird irrational powers. I suppose I should say they really should be non-negative integers because it is okay to have a power of 0. So something like f of x equal to x squared, our favorite parabola that opens upward, has a vertex at the origin, or something like 2x squared plus x minus 3, or something where it's not quite as easy to see that the highest power is 2. Right? You'd have to multiply this out to really be like, oh yeah, if I multiply this out, I'm going to get x squared plus some lower terms. But this x minus 2 squared plus 3, definitely a parabola, definitely has the highest power of x being 2. It's definitely a polynomial of degree 2. Sorry, I read my log. And thirdly, a cubic function, like our favorite cubic function, y equals x cubed, for example, or y equals x cubed plus 2x squared minus x plus 4, or y equals x minus 2 cubed plus 3, or even this thing, y equals x minus 2 squared times x plus 1. Each of these, if you multiply them out, you would see that the highest power of x was 3. These are all polynomials of degree 3, even though it might not be immediately obvious just by looking at it. Although with some practice, I think it can become fairly obvious. Like if you look at this one, if you think about x minus 2 squared times x plus 1, if you multiply that out, you're going to get an x squared times an x, and then you're going to get an x cubed. So with some practice, you can kind of say, oh, like, yeah, that's definitely a polynomial of degree 3. The highest power of x, if I multiply it out, is 3. Questions so far? Okay, let's get to the fun part where we do all the graphing. Well, before the fun part where we do all the graphing, we should talk about M behavior. So the degree of a polynomial and the leading coefficient are two kind of important pieces of information. So if you know if the degree is even or odd, and if you also know if the leading coefficient, meaning the coefficient of the highest power term, is positive or negative, you know a lot about the end shape of the graph. So here are the things I like to keep in mind. If I have a polynomial with an even degree and a positive leading coefficient, there is an example I like to keep in mind, and it's a really easy one. It's y equal to x squared. I know what that graph looks like. E.g., for example. I think that's what that means, right? Close enough. I could have done IE, I suppose. I forget which of those abbreviations you're supposed to use, but we're going with EG because it's a math class and we're not really going to care. So y equals x squared looks like this. And I'm not really concerned what's happening in the middle. I just want to point out that at the ends, either to the right or to the left, the graph goes upwards. So I usually just say it's up on the left, up on the right. Some people like to write other more complicated things like it starts high, it ends high. Or you could even say something like it starts in it starts in quadrant 2. Say that one more time. Oh, sure. Can I? Maybe. I should just put this back in the normal way. Sorry. Trying to do something that I thought was going to work well, but it's not working. Cool. So it starts in quadrant 2 and ends in quadrant 1. So I should be a little more specific there. If we think about the XY coordinate system, this quadrant here is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. And when I say start, so when I'm thinking about graphing a graph, we're usually thinking about doing it from left to right. So we start on the left and we graph the thing as we move rightward. So when I say I start in quadrant 2, it means I'm starting over here. And then as I move from left to right, I'm going to end up over here at the end. Maybe some crazy stuff happens in the middle, but way, way, way to the left, I'm in quadrant 2, and way, way, way to the right, I'm in quadrant 1. This particular graph, nothing crazy happens in the middle, but we could have some things happen in the middle. All right, so what if I put a negative in front of that? What if my leading coefficient is negative instead of positive? Well, then what does a negative outside the function do? It flips it vertically. So it's going to open downward instead of upward. And so way, way, way to the left, well, in fact, I would just think of it as down to the right, down to the left. But other people might say something like it starts low and ends low. Or to be very, very specific, it starts in quadrant 3. It ends in quadrant 4. And what I always remember about even degree polynomials, like x squared or x squared plus 5 or x to the 4th minus 3x plus 1, is that they always do the same thing on either end. They're both up in the end or they're both down at the end. That's it. Yeah.
I don't know, where does it start or where does it end? The left is starting or ending?
The left is starting. So we're always going, so, and this is a very, very broad statement. This is virtually always true. Whenever someone talks about graphing something, they are always thinking about talking about it in the left to right context. So when I say a function is increasing, it means it's getting bigger from left to right. I say a function is decreasing, it's getting lower from left to right. So whenever someone is talking about graphing, they always mean from left to right, unless they are specifically saying something that is not that. Sometimes I will say something like, oh, well, we do this from right to left because there's a good reason to, but almost all the time it's from left to right. So even polynomials or even degree polynomials always have the same thing on at the end, either both up or both down. Whereas odd degree polynomials have opposite things at both ends. So if we have something like y equal to x cubed, which looks vaguely like this, it's down on the left, up on the right. Or you could say it starts low and ends high. Or you could say it starts in quadrant 3. It ends in quadrant 1. That's if you have a positive leading coefficient and an odd highest power, or an odd degree. And then finally, the last possibility is if you have a negative leading coefficient and an odd degree. And that's, again, just going to flip it over. So it's going to go like this. It's not my best graph ever. It's all right. So this one's going to start high. I should say it's up on the left, down on the right. Or we can say it starts high and ends low. Or we could say it starts in quadrant 2 and it ends in quadrant 4. So these are the 4 possibilities. If the degree is even, both up or both down. If the degree is odd, they're opposite. One up, one down, one up, one down. And then if it's a positive leading coefficient, and here I really just think about if it's positive leading coefficient, the right side's up. And if the negative leading coefficient, the right side's down. That's the really, I'm just like it's positive. I know it's going to do a thing. So let's do some practice because while it's nice to know this, we really want to put it into effect. Okay. So, whoops, let's graph a thing. Let's graph f of x equal to x squared times 3 minus x. I don't think you need to fill something like this out every time, but it's nice the first few times. So this is a little bit of a long process, but it's not that long. So let's talk about all the things. The degree of this. Oh, question. Yeah, sorry.
So we've been like graphing these types of functions already though, right? It's just a different format.
Well, kind of. We've been graphing things that don't, so we haven't really been graphing that many polynomials that have a degree 3. We have graphed like x cubed, but we haven't had things where this has more features to deal with.
Okay.
So yes, we've been graphing things. We're just kind of taking it to the next logical level.
Okay.
So this polynomial, if you multiply it out, which we totally could multiply it out. If I multiply it out, I'd get 3x squared minus x cubed. What's the degree? What's the highest power? Right, it's 3. Okay, here's a slightly harder question based on how I've written it. Is the leading coefficient positive or negative? Definitely negative, because it's the coefficient of the thing with the highest power. If I was writing this in the standard way, I would rewrite this as negative x cubed plus 3x squared. So we know the degree is odd, meaning it's opposite. And we know it's a negative leading coefficient, meaning it's going to start high and end low. So it's going to start, I really prefer this. Start high, end low, or it's going to start in quadrant 2 and in quadrant 4. I never think about it that way. It's like it starts high, ends low. So now let's find the y-intercept. So we're going to set x equal to 0. And if x equals 0, y is going to be f of 0, which is going to be 0 times, it really doesn't matter after that, but it's 0 times 3, which is 0. So our y-intercept is 0. X-intercepts, we set the whole y value equal to 0. So we're going to set x squared times 3 minus x equal to 0. And you can either set each factor equal to 0. You say, okay, I know I need to set x squared equal to 0 or 3 minus x equal to 0. But I'm fine with you jumping to the conclusion, which is that, oh, here, if I square root both sides, I'm going to get x equal to 0. And here, if I solve for x, I'm going to get 3 equal to x. And now we come to something new, which actually, I'm going to skip this part for just a second. We're going to go to the number line. We're going to come back to the classifying because you kind of don't need both of these things. On your number line, you want to put the x-intercepts. So my x-intercepts are 0 and 3. And you really don't want anything else. You don't want 0 if it's not an x-intercept. You only want the x-intercepts. So now what we're going to do is we're going to decide, we're going to plug into the original function to figure out if the function is positive or negative in each of these intervals. So let's pick a number larger than 3, like 4, and plug it into the original function. I'm not actually going to find the value. I'm just going to figure out if it's positive or negative. So I plug in 4, 4 squared is positive, times 3 minus 4 is negative, and a positive times a negative is negative. Let's do the same thing in here. I'm going to pick something between 0 and 3. I'm going to pick 1. 1 squared is positive. 3 minus 1 is positive. A positive times a positive is positive. And then pick something less than 0, like negative 1. Negative 1 squared is positive, and 3 minus negative 1 is also positive. So positive times positive is positive. So here's what this actually tells us. This tells us that to the left of 0, the graph is positive. So it actually looks like this maybe. At 0, it touches the x-axis because it's an x-intercept. And then it still remains positive after that. And then at 3, it touches the x-axis because it's an intercept. And then it's going to be negative after that. So doing the number line can actually really be helpful to see what the graph is going to look like. That's that would be a perfectly like reasonable answer for what our graph looks like. The thing above this about classifying the x-intercepts is the following. So x equals 0. It came from x squared, right? We got it by setting x squared equal to 0. That has an even multiplicity because the power is even. So that 2 there, that means we have an even multiplicity. For that factor. Because you have x times x an even number of times. And what that's going to correspond to is at this intercept, the graph is going to bounce. I just like saying bounce, I'm not going to lie. It's fun to say bounce. It's going to bounce off the x-axis, which we can already see happening. Because look, it's positive to the left of 0, it's positive to the right of 0. It bounces off the x-axis. For the other intercept, we're going to have a different behavior. The other intercept, we have odd multiplicity because it came from the 3 minus x raised to the first power, which is an odd power. And when we have odd multiplicity, the graph is going to cross like it does right here because we go from one sign to the other sign. We go from above to below or below to above. So what I would say about this is you can do this either way. You can either do this intercepts and multiplicity thing, which I personally like. I feel like it's fast. Or you can do this number line thing, which kind of almost gives you the graph before you even graph it. Either way is totally cool. I would say you probably don't need to do both, but you can. So now I'm going to plot this graph. And really the only points I'm plotting are the x-intercepts and the y-intercepts. Those are the only actual points I think you need to find. So there's my x-intercept and my y-intercept. I got an x-intercept at 0 and 3, a y-intercept at 0. And then I know the shape of the graph. It looks like this. And oh, look, it is definitely matching up with my end behavior. It's up on the left. It's down on the right. That's good. It should. A couple things. Polynomials should be smooth. There shouldn't be any pointy points. There shouldn't be any jagged edges. It should all be nice. Whoops. It should flow very nicely. Specifically, at this point here where it bounces, it should kind of have a nice rounded out bottom there like that, right? It shouldn't kind of be jagged. And I will also mention that here we have to at some point decide that we're going to turn around to go through that other x-intercept. In calculus, we will learn the tools to figure out where that highest point is. In this class, we don't have them. And so we're not going to bother worrying about where it reaches its local maximum and what that value is. It's just something we don't have the ability to do. Did you have a question, Erica?
Oh, yeah, it's that there are.
Sure, I bet that's what you can ask. Yeah. If you really want to, I don't recommend this, but if you really want to, you could plug in x equals 1 and get the y value, and x equals 2 and get the y value. But I don't need your graph to be that precise. I'm really just looking for all the intercepts and the right shape. That's kind of it. I will say, especially if you're taking 17-8x quarter, being able to take something that looks like this function here, and graph it really quickly to just get this kind of shape is a very important skill. It comes up frequently. So 2 more examples. If I can turn the page. Okay. So now we have another polynomial, which I really don't want to multiply out. right? That's kind of a lot of multiplying, and I really don't need to multiply. In fact, I am preferring to have it in the factored form. That is more useful to me this way than if I knew what it was all multiplied out. So let me ask all of you, show me on your fingers actually, or type it in the chat if you know the answer. What's the degree of this polynomial? Yeah. A little bit more. Yeah. It's definitely a degree 4, because if you multiply it out, if you multiply this out, it's going to be, well, in fact, so here we would have, I'm going to multiply it out a little bit. This part multiplied out would be x squared plus 2x. And this part multiplied out would be x squared minus 8x plus 16. And then if we did multiply it out further, oh, we get an x squared times an x squared, which is an x to the 4th. Really what you can do is you can count up all the powers. This x minus 4 squared gives you 2 instances of x. This x plus 2 gives you another x. This x gives you another x. Oh, that's 4 x's multiplied together to give you an x to the 4th. All right. And behavior. Is my leading coefficient positive or negative? It would be positive, right? Because you can kind of see here if we multiply that, oh, you get a positive x to the 4th. You basically have to look at all of your x's and see, are there any minus signs on them? Like in the previous example, right? If we didn't actually multiply this one out, you can still see that, oh, we're going to have an x squared times a negative x, which will give us a negative x cubed and a negative leading coefficient. So we have a positive leading coefficient. We know things are going to be up on the left, up on the right, because it's an even degree, so they're the same, and it's positive, so they're up. Or you could say it starts in quadrant 2, ends in quadrant 1. Something to get used to seeing. A lot of the time, you're going to have an x, or an x to a power as one of the factors. That's always going to mean the y-intercept is going to be 0. Because when you plug in 0 for x, you're going to get y equal to 0 times it doesn't matter. Because 0 times anything is 0. Okay, I should back that up a little bit. 0 times any real number is 0. There's some limit stuff you'll learn next quarter where 0 times infinity is dicey, but that's not where we're at right now. X-intercepts. So I'm going to set x times x plus 2 times x minus 4 squared equal to 0. And then I'm going to set each factor equal to 0. So this is going to give me x equal to 0. That's going to give me what? X equal to negative 2. And that's going to give me x equal to positive 4. And then I can look at what the multiplicities are pretty easily. X equal to 4 is going to have a multiplicity of 2 because it came from a factor with a power of 2. And x equals negative 2 is going to have what multiplicity? I know I didn't write it. It's definitely 1. And x equals 0 is also going to have a multiplicity of 1. So we know even before we do this number line thing that at 4, it's going to bounce. And at negative 2 and 0, it's going to cross. Which, in my opinion, means we don't really need to do the number line thing, but we're still going to do the number line thing. So let's put all of our numbers. Oh, question. Excellent question. So when I find an intercept, right, because these are my intercepts, right? X equals 4, x equals negative 2, x equals 0. I look at the intercept. I look back at the factor I got it from. Right? I got x equals 4 by setting x minus 4 squared equal to 0. But that factor has an even degree. It's got an even power of 2, so its multiplicity is 2. This factor here, or sorry, this intercept here came from that factor, which has an odd multiplicity. And this intercept here came from this factor, which also has an odd multiplicity. Yeah, but it takes practice. So let's put our numbers on the number line, and we need to put them in the right order. So if I wasn't being careful, I might accidentally write 0, negative 2, 4, which is definitely not the right order. Right? 4 is the biggest, negative 2 is the smallest, and 0 goes in the middle. So now, if I pick a number larger than 4, like 5, and I'm going to look back at the factored form. So I plug in 5, it's positive, 5 plus 2 is positive, 5 minus 4 is positive, the whole thing is positive. Now here's what we could do instead of keeping on plugging in numbers. Instead of plugging in 3, I can say, well, I know that 4 is going to bounce. So if I bounce off and I'm positive over here, I also have to be positive over there. There's no other choice. You could also pick 3 and plug it in and see that you get a positive times a positive. Ooh, times a negative squared makes it positive. So it's still positive if I plugged in 3. And then 0, since it came from a factor with an odd multiplicity, we're going to cross. Or you could pick something between 0 and -2, like -1. If you plug in -1, it's going to be -1 times -1 plus 2, which is positive. So negative times a positive times, this is always positive because it's squared. So a negative times a positive is going to be negative overall. And then finally at -2, we also cross again. So it's going to be positive over here. Plugging in numbers is totally fine. I just find it to be a little bit time consuming. I think it's a good place to start, but after you practice this more and more and more, I think doing it this way, you're like, oh, this came from this. We know it bounces, so we know the sign stays the same. Whereas -2 came from this. We know it's an odd multiplicity, so we know it crosses and the sign changes. Yeah.
So if we're to like say the homework, can we just change to like one of the other?
Yeah, definitely. So we've already kind of got the graph, but let's actually graph it. So the only thing I will say here is I'm going to try and make my intercepts spaced out appropriately. That's kind of it. So I got an intercept at -2, intercept at 0, intercept at 4, and then here's my shape. Oh, and look, my shape is definitely in agreement with what the end behavior should look like. That's always something we should check. So I'm going to be up on the left. I come down, I have to turn around at some point so I can get my next intercept. I'm going to cross through. And then I have to turn around at some point, and I'm going to not cross, I'm going to bounce. So knowing that I'm going to bounce, I'm going to approach this so I can kind of flatten out and bounce off it nicely and then go up like that. And that's the best I can do for this graph with what we have, which is totally fine. Another thing to be aware of, and this is something that's not written down here, but it's totally fine. When you're graphing a polynomial, the number of turns you can have or changes in direction is at most 1 less than the degree. So the previous polynomial had degree 3. And how many turns were there? 2. Right there and right there. And this other polynomial we just did was degree 4. And there were 1, 2, 3 terms, which is the most you could have. Do you have to have that many? No. Can you have that many? Yes. We'll see some, I think we'll see an example. Maybe we might see some examples where you don't have to have that many. So we're flying without the template now. We want to graph f of x equal to x cubed minus 5x squared. Yes. Oh, sorry, question, Tyler.
It's always like,
That's all right. Did I say it's always 1 less?
No, sorry, you said something about like the maximum being 3 turns.
Sure. So if the degree is 4,
Yeah.
the maximum number of turns is 3.
Oh, so that's only under like those circles.
Right. So if the degree is 7, the maximum of the turns is how many? 6.
Okay.
Right. But it might be less.
Okay.
But the most it could be is 6.
Yeah. Okay.
So let's look at graphing this one. Let's write out all the things. So we're going to talk about, here's our technique. We're going to do end behavior. We know that the degree is odd. So the degree is 3. The leading coefficient is positive. That's going to be down on the left and up on the right. Or you could say it starts in Q3 and ends in Q1. Then we talk about the Y-intercepts. So for the Y-intercepts, we're going to set x equal to 0. And we get f of 0 equal to, a lot of these have zeros, the Y-intercept, it's kind of boring. So we get 0, 0 is a Y-intercept. Then we find the X-intercepts. by setting y equal to 0, or f of x equal to 0. And this is where we would like for this to be factored, because solving something equal to 0, you almost always want to factor it. So that's what we're going to do. And I can factor out from x cubed minus 5x squared and x squared. I'm left with x squared times x minus 5. So my x-intercepts are x equal to 0, x equal to 5. Or you might write those as 0, 0, and 5, 0. And now we come to a place where we have to make some choices. I'm going to talk about the multiplicity. So for x squared, we get x equal to 0 as the intercept. The multiplicity is 2, which means we're going to bounce at 0. From x minus 5, we get the intercept of x equal to 5 with a multiplicity of 1, which means we're going to cross. You can also look at the number line with 0 and 5 on it. Whenever I'm doing the number line, I always happen to start as far right as possible. That's just kind of a natural instinct. I don't know why. It's just what I do. I always like to pick a number bigger. Usually, honestly, it's because usually when you start from the right, most of the time everything ends up being positive. It's not always true, but it's often true. So I pick a number larger than 5, like 6. 6 where it's positive, 6 minus 1 is positive, it's positive. Pick a number between 0 and 5, like 1. 1 squared is positive, 1 minus 5 is negative. And then pick a number less than 0, like -1. -1 squared is positive, -1 minus 5 is negative, positive times negative is negative. So we see what we're expecting to see, right? We're definitely going to be negative. We're going to bounce at 0 and stay negative. We're going to cross at 5 and become positive. So I really encourage you to associate in your mind bouncing with the sign staying the same for the function and crossing with the sign changing. So when the graph crosses the x-axis, it changes from negative to positive or positive to negative. When it bounces, it stays negative, negative, or positive, positive. Yeah, definitely. So I would definitely ask a question like this on the quiz, to graph a thing like this and to talk about the end behavior, to talk about all the features.
This quiz is a quiz after
This coming quiz, which is today's Wednesday, right? Yeah, so what we're doing today is fair game for the quiz. Okay. So then we're going to graph it. We already kind of have the graph. I'm just going to throw a 5 out there. Then, oh, sorry. Yes, I can. Woo. And so honestly, I would, if I only had one x-intercept, I might draw it after I drew the graph. So I didn't kind of almost mess up there. I just draw the graph nicely and then, oh yeah, there's my x-intercept. There's no asymptotes for these graphs. Like polynomials never have vertical asymptotes, never have horizontal asymptotes. This does get bigger and bigger and bigger, but it also continues going to the right as well. So it doesn't have a vertical asymptote. So we haven't really gotten to a full discussion about asymptotes yet. But generally, you have a vertical asymptote where a function is undefined. And if you look at x cubed minus 5x squared, it's never undefined. X can be any value, and you get some nice value out. Horizontal asymptotes we get when the function values as x gets very, very large get close to a particular number. Like with our exponential functions, when x gets really, really negative, the function gets really, really close to 0, which is why they have a horizontal asymptote there. These functions, that's not going to be the case, because for this function, if x gets really, really large, the y values just get larger and larger and larger. And if x is really, really negatively large, the y values just get negatively larger and larger and larger. So very generally, polynomials never have asymptotes. Never have vertical asymptotes, never have horizontal asymptotes. They're kind of our nicest functions that we ever get to deal with. They have all the things we want. They're nice and continuous, but there's no breaks in them. They're also differentiable, which I would just think of as being smooth, right? There's not any jagged edges, and they have no asymptotes to deal with. So they're pretty great. Let's look at another example. I'm going to change this example. I don't love you, x cubed. You can go away. Yes, I can. You guys didn't even know. I'm going to change this example to have. Sure, we'll make this fun. Okay, so let's look at this example. X minus 1 times x minus 3 squared times x plus 1 cubed. We're going to do the same stuff. To find the, well, first we're going to find the degree. The degree is how much? I think I heard someone say the right number there, 6. Right, because there's an x to the first, an x squared, and an x cubed. And you multiply those together, it's x to the 6. Or really, you're adding the powers together. 1 plus 2 plus 3, 6. Well, I shouldn't say multiply there, right? Because 1 times 2 times 3 is also 6. But 1 plus 2 plus 3 is 6. So right, we're saying we've got 3 instances of x, 2 of x, 1 of x. And if you multiply all those x's together, you would get x to the first times x squared times x cubed, which is x to the 6. Because you're adding the powers. Leading coefficient. Well, none of those x's have, none of those x's have a negative, so definitely positive. So we are up and up. Or Q2 to Q1. You could never think of it that way. It's fine to think of it that way. It's just not the way I think of it. All right. So then let's talk about the y-intercept, which is not going to be 0. So if we set x equal to, right, I did change the function, right? Everybody just said, everyone's clear, right? It's x minus 1 times x minus 3 squared times x plus 1 cubed. If we set x equal to 0, we're going to get y equal to 0 minus 1 times 0 minus 3 squared times 0 plus 1 cubed, which is -1 times positive 9 times 1, which is -9. Okay, great. And then let's find the x-intercepts. So we're going to set the whole thing equal to 0. X minus 1 times x minus 3 squared times x plus 1 cubed equal to 0. And then we're going to talk about the intercept. So from this first factor here, what's the intercept? +1 with a multiplicity of 1, which means it's going to cross because it's an odd multiplicity. And from x minus 3 squared, the intercept is x equal to 3 with a multiplicity of 2, which means we're going to bounce. Cool. And then from x plus 1 cubed, the intercept is x equal to -1 with a multiplicity of 3, which means we're going to cross. And again, if you wanted, you could totally do the number line, putting 3, 1, and -1 on it. And I'm going to use this information I've already gathered here. I'm going to start over way to the right because that's, I know I say we start on the left, but whenever I do the number line, I just start on the right. I guess I can start on the left. We can pick -2. So pick -2 and plug it in. I get a -2 minus 1, which is negative. A -2 minus 3, which is negative, but it's squared, so it's positive. So I get a negative, a positive, and then -2 plus 1 is negative, and it's cubed, so it's still negative. So with a negative, a positive, a negative, overall it is going to be positive. Right? Negative times a positive times a negative is positive. If you have an even number of negatives, it ends up being positive. And then instead of doing that 3 more times, I'm going to just say, well, I know that at x equal to -1, it's going to cross. So it's going to go from being positive to negative because it's going to cross. Oops, yeah, that's right. And then at +1, it's also going to cross. It's going to cross back over to being positive. And then at 3, it's going to bounce. So it's going to bounce and stay positive. And I'm happy about that because it looks like my end behavior is right. It's up on the left, it's up on the right. So I'm good with that. Also, I should mention here, how many turns does it look like I have? It's like 3. So places where I change directions, instead of going down, going up, instead of going up, going down. It looks like I have 1, 2, 3 turns, or you'll say 1, 2, 3 highest or lowest points. So it looks like I have 3 of those, which is definitely way less than 5, which is the maximum number I could have. So you don't always have to have the maximum number. You might have less than that. All right, so here's what this one kind of looks like. I've got a -1, got a 1, got a, and I'm going to come down. So I'm going to just go through -1, 1. Oh, and I also have to hit the y-axis at -9. I'm not going to be too strict about that. So here's what I'm going to do. I'm just going to graph it. I'm already starting off bad. All right. So, okay, fine. So my y scale, maybe not so great. That's okay. It's really okay. Because we found the y-intercept, right? When we plugged in 0 for x, we got -9 for y. If I was trying to draw this more precisely, I might have been a little more careful with my starting point. I might have said, okay, I'm gonna start more like up here, kind of come down very steeply, and then do like that, and then like that. That looks a little bit more realistic as far as being -9, but it's not super important. This graph would totally get all the credit you could possibly get for graphing something like this. So don't worry too much about the y scale being right on. It doesn't need to be. Okay. So then we kind of tack on some other stuff here at the end. Even and odd functions. So when I think of an even function, I think of y equals x squared. It is symmetric about the y-axis. If you flip it over, it looks the same. That's my #1 even function example. An even function has symmetry about the y-axis and satisfies this equation, f of -x equals f of x. So for example, f of x equal to x squared. An odd function has symmetry that's a little stranger, has symmetry about the origin, also called rotational symmetry. And my prime example is f of x equal to x cubed. If you think about x cubed, if you rotate it 180 degrees, it still looks the same. Or alternatively, instead of thinking of rotating 180 degrees around the origin, you can also think of reflecting it vertically and horizontally. So if you take x cubed, reflect it vertically, then reflect it horizontally, order doesn't actually matter. It looks the same as it started. Oh, I think I killed this pen. Oh no. So if you think about x cubed, if you flip it over, it looks like this. That's flipping over the x-axis. And you flip it over the y-axis. Oh yeah, it looks the same as it started. I mean, the same, right? Assuming my graph is actually right, but you get the idea, right? This flipped, looks the same as you started with. Flipped over the x, flipped over the y. And the equations we have to satisfy to be even, the even one I think makes a lot of sense. Because the even one, we're just saying, oh, if you replace x with -x, right, which is flipping across the y-axis, it should look the same as the original function. This one also, we're saying, oh, if you flip it across the x-axis, sorry, the y-axis, or if you flip it across the x-axis, it should look the same. So think about this graph here again, x cubed. If I flip it across the x-axis or across the y-axis, it's going to look like that. That means it's odd. Or you could say in your head, if you rotate this 180 degrees, it looks the same as when you started. Let's look at some examples. So how do we show a function is even? It's not as bad as it sounds. F of x equal to x squared, we know is even. It looks even. It has the usual even symmetry. Showing it is not that bad. We're going to say, well, I want to show that f of -x equals f of x. So I'm going to replace x with -x. So if f of x equals x squared, then f of -x is going to be -x quantity squared, which you could actually write as -x times -x, which is positive x squared. And oh, look, that's the original function. that shows it's even. So to show a function is even, you do have to show that this is true for every x, right? We didn't just pick a value. We didn't say, oh yeah, like f of 3 is 9 and f of negative 3 is also 9. It might be even then, but this is the work we actually need to show a function even. And we can do it for g of x as well. To show g of x is even, well, I'm going to look at g of negative x. I'm going to have 2 times negative x to the 6th minus 3 times negative x to the 4th plus 1. And you might recognize here that each of these powers are even powers. And when you take a negative thing raised to an even power, it becomes positive. And negative x times 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 negative x is positive, because it's an even number of negatives. It's positive x to the 6th. And negative x to the 4th is positive x to the 4th plus 1. And that's the same thing we started with. That is the function g of x, which shows that that function is even. Okay. Right. So I'm changing the x. So I would say I'm replacing each x with negative x, and then I'm asking the question: is the function the same as the function I started with? Is g of negative x equal to g of x? On the other hand, to show something's odd, there's kind of 2 different ways you can do it. Here's the way that's actually probably better than what I usually do. First, we're going to look at f of negative x. And that's going to be negative x quantity cubed. And the negative thing to an odd power does retain the negative sign. Negative x times negative x times negative x is negative x cubed. And at this point, you might just be able to be like, well, hey, that is definitely equal to negative f of x. But another thing you could do instead is also just write it down. Negative f of x is negative x cubed. And oh yeah, those are the same. So we can say that f of negative x equals negative f of x. And I kind of like that better than what I usually do, which is kind of factor out a minus sign. Let's look at the next example. So this next function is a little more complicated. We have g of x equal to x to the 5th times the square root of x to the 4th plus 9. And that's going to be, so g of negative x is going to be negative x raised to the 5th times the square root of negative x raised to the 4th plus 9. And here's the thing you really want to get used to seeing in these sorts of problems. Negative x to an even power, you're going to lose the negative. So inside the square root there, it's just going to be x to the 4th plus 9. On the other hand, negative x to an odd power, you're going to keep the negative because it's multiplied by itself an odd number of times. So I'm going to get a negative x to the 5th. And then if I look at if I look at negative g of x, that's just a negative slapped in front of the whole function. Which, oh yeah, that's the same. So yeah, check. They're the same. So we have shown that g of negative x equals negative g of x. I know it's 10:51. I'm going to ask you for an extra minute just so I can show you one more problem very quickly, and then we'll end it. So let's actually do this second one on this page here. Determine whether this function is even, odd, or neither. So here's the process, because we don't know. Lots of functions are even, lots of them are odd, but lots of them are neither. So here's what I would recommend doing. First, check for even. So I'm going to look for f of negative x. It's 2 times negative x to the 5th plus 3 times negative x squared plus 1. Simplify it. That's going to be a negative 2x to the 5th plus 3x squared plus 1. And then ask yourself, does this equal the original function? No. So it's not even. Okay. So then we have to ask ourselves, okay, well, does this equal, oh, sorry, yeah. Sorry, things, yeah. So then we have to ask ourselves, okay, does it equal negative f of x? Well, negative f of x is just a negative out in front of the whole thing. And if we distribute that, we get negative 2x squared minus 3x squared minus 1. Are those the same? No. So it's not even. I'm sorry, not odd. So it's not odd and it's not even, and it's neither. So this function, f of x, is neither even nor odd. Thanks for the extra minutes there. I appreciate it. Oh, you're welcome. Of course. Here's where this one's a little tricky, actually. If I want to distribute this negative, I can't distribute to the top and the bottom. So that's like multiplying by -1 over -1, which is +1. So I really want to think of this as -1 times x squared plus 1 over 2x cubed. Sorry, 2x to the 7 minus x cubed. And I'm going to think of this -1 as 1 over -1, which is totally equal to -1. 1 divided by -1 is -1. The reason why is because I know I want the top to look like x squared plus 1. It's the bottom that looks a little different. So I'm going to multiply the top by 1, the bottom by -1. Wow, my numbers are looking terrible there. And when you do that, 1 times x squared plus 1 is x squared plus 1. And -1 times the bottom, you distribute, and you get -2x to the 7 plus x cubed. And that is equal to negative f of x, right? That's exactly what we have up there. So this does equal negative f of x. So yes, it is odd because f of negative x equals negative f of x. That's how you do that one. Because I knew what I wanted. So I was trying to make it look like this. And I had -1 times this. I knew I wanted x squared plus 1 to stay the same on top. So I didn't want to multiply by -1 over 1. Because -1 over 1 would give me a negative x squared minus 1 on top, and the bottom would still be what it was. So I used my knowledge to be like, okay, I know I want the top to stay the same. I should, if I'm going to multiply by -1, when you multiply a fraction by -1, you can either multiply the top or the bottom by -1. And I decided that we need to do the bottom so it looks like it